Hi everyone, I am Shantanu. I am going to discuss our paper titled as Information Theoretically Secure and Highly Efficient Search and Row Retrieval. This is a joint work with several universities. So secure data outsourcing is a classical problem where a database owner outsources its data in the ciphertext form to untrusted cloud, on which user computes their queries and retrieve the answer in ciphertext form. The techniques for secure data outsourcing can be broadly classified into two different categories. The first one is the computationally secure. Most of the encryption techniques belong in this category. These techniques are secure under the computational capability of the adversary. If the adversary has infinite amount of computational capabilities, these techniques can be broken and adversary can learn the ciphertext value. These techniques use only one cloud server to store the data. Microsoft Always Encrypted and MongoDB are the examples of such industrial systems. On the other hand, the second class of techniques known as information theoretically secure techniques. Secret sharing is the best example of such techniques where the database owner create secret share, or you can say partition the data into multiple secret share and place them into more than one non-colluding cloud servers. Since here the data is divided into multiple parts, a single cloud server cannot learn the underlying ciphertext. And these techniques are also known as secure regardless of the computational capabilities of the adversary, means secure forever. Several companies are developing database systems under this secure model, such as Galua, Cybernetica, and Stealth. Since these techniques provide the highest level of the ciphertext security, our paper focuses on this type of secure techniques. Before going to our problem statement or anything else, let's discuss what is the meaning of secret sharing techniques. There are multiple types of secret sharing techniques, such as given by Adi Shamir, known as Shamir secret sharing techniques, additive share, Boolean share. So let us discuss a few of them. So first one is the Shamir secret sharing. This technique is given by Adi Shamir. So consider that on a graph paper, we are given a single point. And if someone will ask how many lines we can draw, the answer is infinite number of lines. However, if we are given only 2 points, then the answer is only one line we can draw passing through these points. And whenever this line crosses the y-axis, this is the secret value. So for example, consider that a database owner is Alice. She has secret value 5 and she wants to distribute the secret value 5 using Shamir secret sharing to two non-colluding parties known as Bob and Carl. So she will draw a random line passing through y equal to 5 and select any two random points. So for example, here she selects 9 and that is given to Bob and another point 7 that is given to Carl. These Bob and Carlson do not collude with each other. They can never learn the secret value 5 of the Alice. But whenever Alice wants to learn back the secret, she will get the value back from Bob and Carl and perform Lagrange interpolation. Another type of secret sharing is known as additive secret sharing. Alice divides her secret value into two parts, such as addition of two values. So for example, here 5 is divided into two parts, 3 and 2. 3 is given to Bob and 2 is given to Carl. Again, since Bob and Carl are not communicating with each other, they cannot learn the secret value 5. And whenever Alice wants to learn back the value back, now here in this case, instead of performing Lagrange interpolation as you saw in the last slide, she will just add two values. Very simple operation. And she will get the secret value 5 back. Following these two types of secret sharing techniques, multiple types of system have been developed and these system can be classified into two further categories. One category where servers will communicate with each other to perform the query. And another category is one where server do not communicate throughout the query processing. So under first category where server communicates, Galua is developing their system and recent system by Boston University in NSDI known as Secrecy and ShareMine, they require servers to communicate with each other. On the other hand, SSDB, Obscure, these are the system where servers do not require communication for the query processing. The important point here in both these techniques is that both such technique can support selection queries. However, these techniques, both these categories comes with some disadvantages. So in the under first category where server communicate with each other, if server will communicate, there will be significant overhead. And moreover, they communicate multiple times during the query processing. Furthermore, they reveal volume. The volume is the size of the query result. On the other hand, the non-communicating techniques are susceptible to volume leakage, and they are also prone to access pattern leakage, meaning they reveal the identity of the rows that satisfy the answer. Furthermore, these techniques may require client to store significant amount of data, or these techniques require more than 4 servers. So our goal in this paper is to avoid the disadvantages of these techniques and develop complex selection queries for disjunctive and conjunctive search using secret sharing. That is under the efficient operation, secure, they will not reveal access pattern, they will not reveal volume, they will not require communication among the server. That's why we will get the performance, and they require minimum amount of work at the user side to get the answer back. To do this entire such thing, in this paper we propose a system called as S square, that is known as information theoretic secure selection. It is based on 2 rounds. In the first round, first we need to know the row IDs for the query predicates. And in the second round, based on the row IDs, we retrieve the desired row. So for example, if we want to perform a single predicate search over a single column, then we use additive share. If we are doing conjunctive search, we again use additive share. If we are using disjunctive search, then we use multiplicative shares or Shamir secret shares. Here is the performance. So since we are avoiding the communication and doing something extra for the string matching operation, you can see the performance result. S squared takes less than 2 seconds for doing any type of selection queries, while the other system that are performing the same query, they take significantly more amount of time. These results are carried over 1 million rows of TPCH line item table using one thread. Details can be seen in the paper. Now from here, I will cover a few things. I will cover first how we outsource data to the cloud, then how we will execute single column keyword search, then conjunctive search and experiment. There are several other details that are given in the paper. The first one is the disjunctive search, range search, and group by queries, and several additional experiments. So for these things, you can refer to the paper. So first go over the data outsourcing. Let us consider here there is a table patient containing 2 columns, name and cost, and row ID we are adding just for simplicity. And one more thing here, throughout the presentation, I am using only name containing 2 letters, but this is not the restriction of our approach. We can handle different length of the string, and for details, please refer to the paper. So first thing is this, according to the English alphabet dictionary, we convert all the string to their position. So for example, J is the 10th letter. So we convert the first J to the 10th and O equal to 15. You can see the first row. 10, 15, and the cost will remain same as since this is the numeral value. After this, for each number, for example 10, 15, and 4 in the row number 1, we create additive share and multiplicative share. These additive share and multiplicative shares are outsourced to 4 servers. You will see later that why we are using 4 servers, and this is the maximum number of servers we will use throughout the any type of computation. Now let's go over the single column keyword search. The query is to retrieve all the rows containing name equal to Joe in the patient table. So to do this part, what we will do in the first round, we need to know the row ID that is corresponding to Joe. And in the second round, we need to fetch all those row IDs. So before showing you how we will work over the strings, let's go over something that is known as fingerprint function. This is defined for the string matching over clear text values. This is given by a function over some modular function. And now let us consider with the help of one example. So here example is, let's say Joe. So how we will compute the fingerprint function? First, we need to represent Joe into numbers. So according to English alphabet dictionary position, we convert J to 10 and O to 15th position. On top of this, we compute the fingerprint function. Here the length of the string is 2. We select some parameter, P is the modulo parameter that needs to be prime, and R is the finger function, and we based on these numbers, we put the values fingerprint function, and we get fingerprint value for Joe that is shown in the last box, 19,135. Now let us consider why we are using fingerprint in our paper. So fingerprint functions are additive homomorphic, and moreover additive secret sharing is also additive homomorphic. So what is the meaning of this? So let's say fingerprint of Joe at the database owner side is 19135, and she wants to store at two different clouds. So database owner can create two different values of this part in a random way and store at the cloud. If the user wants to search Joe, she will also create the fingerprint of Joe, and after that she will also create two different values. These values are given to the server, and servers, after subtraction, it will provide the final answer to the cloud, to the user. After getting this value from the cloud, the user will perform the addition operation, and if it will get 0 means the value is stored at the server, otherwise not. So that's why, because it can perform string matching operation for us over additive shares, we are using in our work. There are two properties: that it can compress large string to a number, and second thing, two different string produce two different fingerprint with a very high probability. So now let's go back to our part, how we use fingerprint in our search operation. The first step is at the user side to create the secret share of Joe according to, first convert the name Joe according to English alphabet dictionary position, and then create additive share. And on top of these additive share, user will create fingerprint. Since we are using two server for this operation, user will create two fingerprint, F1 and F2. These fingerprints are sent to server 1 and server 2. The blue color column is the additive share. After this, the server will compute on additive share the fingerprint function using the same modulo function. After this, the server will subtract the fingerprint received from the client, and it will produce two vectors. These are here. These vectors are sent to the user. After receiving the vectors from the cloud, the user will perform the modular addition, and it will get either 0 number or a random number. If 0 will appear, that means the value is in the database, otherwise value is not in the database. And the position of 0 will represent the row ID where the query predicate has been obtained in the database. But then we need to fetch the desired row IDs. And this operation we are not showing due to time limitation. Now let's see how we can use fingerprint in conjunctive search also. So here the conjunctive search is asking, give me all the rows where name equal to Mo and cost equal to 6. And in this example, only the row number 2 will satisfy. Again, there will be two rounds. In the first round, we need to know all the row IDs. And in the second round, we need to fetch the desired rows. So here, the user will again create only single fingerprint for a single server. So first he will convert the query predicate into additive share, and on top of these, it will compute a fingerprint. So note that here, we are using two query predicate, but only single fingerprint is generated for a single server. These fingerprints are given to the server. So here we are showing you only one server for simplicity. Server will take the desired column in the additive share form and compute the fingerprint function. After this, the server will subtract the received fingerprint from the client, and it will produce some value. These values are given to the user. User will perform the modular addition operation. Again, it will provide the random number or value 0. If it is 0, that shows the matching desired row for the corresponding query. So for our experiment, we selected the TPCS data of 1 million rows and 10 million rows of line item table. We selected 4 AWS servers, and the same machine was used for database user. So here is the result of the scalability. If we are using 1 million rows or 10 million rows, the corresponding time for S square is less than half second using 4 thread over 1 million rows, and less than 4 seconds on 10 million rows. So this shows that our system is really for any type of operation. We provided S square, that is efficient and scalable technique for selection queries using both additive and multiplicative secret sharing techniques. Our techniques hide access pattern and also hide the volume for the query. It supports conjunctive search, disjunctive search, and row retrieval. Furthermore, other operations such as disjunctive search, row retrieval, and group by query and several experiments are given into the paper. Please refer to the paper. Thank you.